All right, welcome back, everyone. I hope you had a good lunch. And if you're starting to feel sleepy, don't worry, we're going to talk about AI on Kubernetes, which is like caffeine for your brain. And if you need more energy, they're giving like Guaraná shots upstairs, one of the sponsors. So I really recommend it. Let's get started. So imagine this. Kubernetes is a personal trainer, the personal trainer for the cloud, which is strict, reliable, and great at scaling things up. And AI, on the other hand, is that genius friend, super smart, a little bit unpredictable, and constantly snacking up on GPUs. And now these two are hanging out more than ever. They're working together, and they're getting seriously powerful applications up and running. Now, one of the most exciting things, results of this partnership, of this friendship, is something called RAG, so Retrieval Augmented Generation. RAG systems gives your LLMs access to real dynamic knowledge by connecting it to a vector database. Think of the vector database as your model's short-term memory, where all the relevant facts live. But if that memory fails, then a lot of things come to a halt. So, your LLMs start hallucinating, might give you wrong answers, or just go completely blank. So today, we're going to talk about how to disaster-proof the vector database, especially when you're running it inside Kubernetes. Now, let's do a quick raise of hands. Raise your hands if you're working with applications with AI. Anyone? A few people. Okay, great. And keep raising your hand if they're running on Kubernetes. Okay, not so many. And if you have vector databases with there, are you backing them up? Anyone raise your hand? Okay, just one person. So that's why we're here. If you raised your hand for 1 and 2, but not 3, you have a problem. So many teams put vector databases in production, but they forget to back them up. And this is a big problem, and I'm here, to raise awareness about that. I'm going to repeat that a lot. But, you're going to watch throughout the presentation that is going to be, it can be something simple that you don't have to think too much about. Now, before continuing, let me introduce myself. As you saw at the beginning, my name is Julia. I'm a global technologist at Veeam. We do a lot of data protection. That's why I decided to give this talk. Also, I was inspired by two colleagues, Pavan and Sweta, who talk passionately about this topic, and I think it's important. I'm also a CNCF ambassador. I'm an AWS container hero. I organize a lot of events in New York. I live in the US, and if you're ever around there, hit me up. We have a lot of events, things going on. And over the past years, I've seen a shift. Teams using AI in production. Obviously, we talk a lot about AI everywhere. At KubeCons, it's one of the biggest topics at other conferences as well. But few of them think about backup and recovery until it's too late. Now, let's talk a little bit about RAG. AI applications that use vector databases to retrieve relevant information are known as Retrieval Augmented Generation, or RAG systems. RAG is one of the most powerful architectures for grounding large language models, so LLMs, in real dynamic data. Rather than relying solely on static pre-training, the LLM is enriched with contextual documents retrieved from the vector database. So, this is how it works in practice. You begin by ingesting enterprise data from the knowledge base, so it can be PDFs, support tickets, or any other knowledge document that your company may have. And that data is broken into chunks and passed through an embedding model. The embedding model converts each chunk into a vector, capturing its semantic meaning. Then, when a user submits a query, it's also embedded into a vector and used to search the vector database. The vector database returns a set of similar vectors, essentially the most relevant chunks of information based on semantic similarity, based on what the user put it. And then, finally, these retrieved vectors, they serve as context for the LLM. So it helps generate a response that is accurate, relevant, and grounded in real data, which is then streamed back to the user. In our demo, at the end of this, I'm going to do a demo, and we'll be using a similar architecture to this one. And we'll see that without this contextual data, the input from the vector database, the LLM could, hallucinate. It could produce incorrect information, which not only degrades the user experience, but it's dangerous for businesses because it can disrupt your business operation. It stops working, and then customers start complaining. So we don't want that. That's why we're all here trying to learn more about this. Now, throughout the time, we've used different types of databases. You're probably familiar with some of these. So we've had key value stores for fast lookups. We've had document databases for semi-structured content and graph databases for relationships. But now we're dealing with a new type of database, totally different problem, which is meaning. That's what we're focusing on. And we're not just storing values. We're storing context, we're storing semantics, and we're storing intent. And that's where vector databases come in. So instead of structuring the structure rows or documents, the vector database, they maps data points into multidimensional space, like you can see here. So if you embed the word, let's say, banana, it will likely land near apple and orange and not dog or sparrow, because it understands, that spatial closeness represents semantic similarity. So when you search, for example, on Google, apple taste, or let's say ChatGPT, apple taste versus apple valuation, the search engine will know that one refers to the fruit and one refers to the company. Why is that? Because the embeddings for those two meanings of apple are located far apart in the vector space. And Google's vector system picks the one that's closest to your intent. And this is what helps the LLM to ground its response in real, relevant information in real time, instead of making things up. Now, plenty can go wrong with vector databases. I've seen teams lose vector databases due to a lot of reasons. So could be because of a node or volume failure. Maybe your pod's VPC got wiped or your node crashed. Maybe because accidental deletion. This is one of the most common reasons. And we never think that might happen. But yeah, maybe someone dropped the production database instead of the development database. So that's very common. One of the biggest reasons for databases stop working. Also, ransomware attacks, they're becoming very sophisticated, very common. At Veeam, we deal with that with companies that are victim of ransomware attacks every day. And we've seen that, now companies are being hit more than once, twice, and repeated over and over again. So this is another topic for another talk, but, that's very common. And, index corruption as well might be something, which means your vector search stops making sense, and misconfigured reclaim policies. So, that's a permanent loss. You can't get that back up and running. And that's why it's important to protect your vector databases. So it needs solid backup and recovery strategies, because when things go wrong, you don't want to be in that situation of the meme, everything is fine. It's not fine. And you need to think ahead before that the problem happens. So protecting vector databases ensures integrity, it ensures fast recovery, cost saving as well, because, if something happens, you can recover fast and things are working again, and a reliable user experience. Now, protection, again, has different flavors. Like we know, databases have different flavors. It all depends on your use case. But there are a few types of protection for your databases. So one of the most common and usually the simplest one is using storage level snapshots. Now, depending on how your vector database is deployed, the data might be written to persistent volumes, so typically using PVCs in Kubernetes. If that's the case, you can use CSI snapshots, and those, they take low-level crash consistency copy of the data. Those snapshots, they are fast, they are efficient, and infrastructure managed. But they are not enough. Usually you need more than that, especially if you're running AI workloads in production and you need application consistency or you need fine-grained restore. So this is just, I would say, the basic. Another option you have, if your applications need a higher level of data protection and data consistency, is to making the application aware of those snapshots. So by introducing data hooks, data service hooks. These are small press and post snapshots, steps that help coordinate things. So for instance, before taking the snapshot, your application freezes or flushes the data to the disk, then it ensures that it is in a clean and consistent state. It takes the snapshot, and finally, it unfreezes the service. Now, this flow, freeze, take the snapshot, and unfreeze, ensures that your backup isn't capturing in-flight writes, and it's not, have finished, or, it has inconsistent data. Another option as well, a third option, and often this is more precise, is to use data service level tools for backup. So instead of relying on the storage layer or coordination hooks, you let the database itself generate a consistent backup. And these include tools like PG dump for Postgres, or MySQL dump for MySQL, or Mongo dump for MongoDB. Each database has its own flavor as well. And these tools, they are aware of the database internals, so the snapshots are clean, consistent, and application accurate. And finally, there is another option, which is a mix of all these other options that I gave you. It's a combination of all three. For example, you have a MySQL using MySQL dump, you have a Postgres using CSI snapshots, and for other services, you have those coordination hooks. And each component might have, different consistency needs, data volumes, and restore priority. So the reality here, you need to know what your business needs. What are your RTOs? What are your RPOs? And also how your data, how volatile your data is, and how much you need to protect it, how fast you need to restore it. Is that data as important, or can you lose it and then you can just build it again? Those are things you need to talk to your stakeholders and decide in a group, and then see what are the technologies that are going to help you with that. And there is one tool, one open source project that can help with all of that and manage all those snapshot types that I just talked about in a unified way. And it's called Canister. Vim actually is the one that started building it, and then after donated it to the CNCF, and now the community is helping, build more, make it better, with contributions from the community. And it's very simple. So if you give it a simple declarative way to define and execute operations like backup, restore, or delete those snapshots, it can do those in a matter of blueprints. So same as YAML files, you can have those blueprints and use in a CI/CD if you need. And all those are through CRDs and Kubernetes APIs. It's super easy to get started. I'll show a little bit of Canister in the demo, but if you have questions, I've been contributing a little bit, and you can find the documentation, or you can look it up yourself. Now, just to give a quick example of how it works, let's say we have a vector database workload running in our Kubernetes cluster. So, for instance, PG vector, and we deploy the Canister controller there. Now, then we apply what I called a blueprint, which is what we create. We write that blueprint. I mean you, anyone can write different blueprints to protect the PG vector instance. And then the blueprint defines exactly how to back it up, where to store the backup, and how to restore the data if needed in the end. And all of that through Canister's native CRD. Next, wait, because I'm thinking it's falling here. Oh, good. Next, we create an action set. So this resource tells Canister how the controller, what the controller needs to do. So it tells it to go back and look to the blueprint and execute a specific task. Usually it's defined as a kube task, and that task might be a script or a command that runs inside a pod or a container, and Canister managed all the execution for us. Finally, to run the task, Canister uses something called the Canister function, and this function talks directly to the vector database using environmental variables, secrets, and service definitions that we pass in. Canister also includes a lightweight CLI called Kendo, which handles the data movement for us during the workflow. And after we take all the database dump, so we do the backup, Kendo is used to push the data, that backup, to an object store that you can decide where you want it to be. Could be like S3, GCS, or any other location of your preference. And then once the entire operation is complete, whether it's the backup, the restore, or you can choose, to delete everything, the Canister controller updates the action set with the outcome, and the action set acts actually as a status dashboard for that workflow. So it gives us all the logs, all the information, if things were complete, if they are still in progress, all the phases for detail and detailing each step. We'll see that throughout the demo. Now let's take a look at this demo. So let's see all of these in action. So end-to-end example of how to use Canister to protect the vector data. And this demo is actually it's a book nest application. So for books, anyone that likes to read here, it's for a book recommendation that lets users ask questions and gets answers based on book themes. And behind the scene, it's powered by a vector database that holds information on 175 books. And each book description is all actually embedded in a 384-dimensional vector, as I showed you the vector database, using the BAAI embedding model. And here we're also using PostSQL as the database with the PG vector extension. And I chose this because it's open source, widely used, and if you're already familiar with Postgres, using PG vector is very easy to get started. You just enable the extension and you're good to go. Now, this is the architecture and behind the demo. I tried to keep it simple, but because I haven't included an LLM, like in a full reg setup, because here the goal is just to talk about the vector database and focus on the vector data layer. The cluster is split actually in two namespaces, so the PG vector and Canister. In the PG vector namespace, we have the book nest application, which is our book recommendation chatbot, and this is exposed via ingress and a service, making it accessible to the users. There's also a config map that holds two key things. The book knowledge base, which is where the description of all those 175 books are, and the embedding model, which is used to convert those descriptions into vector form. And of course, we have the Postgres stateful set running the PG vector extension, which serves as our actual vector database. And in the Canister namespace on the right, we have the Canister controller, which manages all the data protection workflow. And there are two key custom resources in there. So we have the blueprint, which I'll show you. It defines the backup and the restore logic. And we have also a profile, which contains the credential and the target location for storing the backups. Now, let's get started. So we'll start by submitting a sample prompt into the application window. As you can see, the vector database will return a set of suggestions that are relevant to the theme we provide. So this is just an example. We could put anything there. But these results are important because we'll see later in the demo that even after a disaster, the results will remain consistent. And this shows that the backup and restore process preserves everything as expected, which is what we want. We want to have that peace of mind. Now, let's take a look at the running pod. So let's change the screen. Wait. Yes, now let's see the running pods in the app namespace. So we have a few key components here: the PG vector, the chat deployment pod, the Jupyter notebook pod, which we use to input data in the Postgres, and the Postgres pod itself. Next, we'll enter the Postgres pod and connect to the database using pSQL, and we'll log in with the user for Postgres, and we'll connect to the app database. Now, let's list all the available databases here. And here we can see the application database includes a table called documents, which stores all our book vectors. Now, we'll run a sample query on the documents table. And in the output, we'll see there will be several columns, so ID, author, title, description, and so on. And most importantly, we see the vectorized version of the description. So I'll scroll down, and there are 384 dimensions, meaning 384 floating point numbers that represent the vector embedding for that text. Great. Now, let's switch over to the canister namespace and take a look at the pods running there. We can see that the canister operator running is, which is the controller responsible for running the blueprint-defined workflows. So let's see the pod. There it is. And now we'll look at the secrets in the app namespace. There are two. So there is PG secret. Let's get secrets, yes. So we'll see there is PG secret, which is used in our blueprint to connect securely to the Postgres database, and S3 secret that contains the AWS S3 access and the secret keys used by Canister. Now, next we'll check the Canister profile that has been created. This profile is what tells Canister where to store the backup and how to authenticate. So we can see the YAML output that shows everything the blueprint needs, the bucket name and path, the secret name, and key fields inside, so the region as well. It gives us all the information. This was already created. Now, let's check if there is any existing blueprints in the Canister namespace. And we'll see there are no blueprints yet, and we're going to create a new one. So let's take a look at how the blueprint is structured. This blueprint here defines how to run a backup, a restore, and a delete workflow. And since it's a Kubernetes custom resource, the top section has the usual metadata. Then we move into the core blueprint part. So starting first, key action is backup. And the backup action defines an output artifact called cloud object, which contains a key value pair, which tells us where the backup file will be stored. In the same location will be used again, so we'll use this information for the restore and the delete process. Then we use a kube task to dump the content, and then to handle this authentication securely, we use a custom image, we're past that already, and now the command section. First, it sets the required environment variables like PG host, PG user, and PG password, and then it runs PG dump all, pipes the output into gzip, and finally it uses Kendo to upload the compressed dump into the cloud. Now, let's move. The restore action is very similar. So this step reuses the cloud object artifact produced during the backup and contains a single phase called PG restore. And the structure is very similar. Instead of using dumping the data, it actually pulls the backup file using Kendo, decompresses it using gunzip, and restores it into the database. And there is also a set command to patch local settings into the dump. Finally, at the bottom, also, we can see all the commands that, they are very similar to the backup one. And finally, at the bottom, we had another action, so a third action, which is the delete action. And very similar, you can see it's reproducible, so you can, just copy, paste, and change whatever you need. Now that we created the blueprint, the next step is to start running the backup. So one important thing to note is that when triggering the backup, we need to specify the name of the S3 profile that I just showed you. And then to kick off the backup, we'll use a CLI tool called canctl, which is a command line interface built for Canister. Then it creates an action set for the backup action. We specify the namespace as Canister. We use the blueprint we just created called Postgres BP. We target the stateful set that runs our Postgres vector database. And along that, we pass in the S3 profile. And then once this runs, we see the action set has been successfully created. And at this point, the Canister controller detects a new action set, and it begins executing the backup. And a few seconds after, we can see the backup is marked as complete, success, and it means the Canister controller finished the operation successfully. Now, if we describe quickly the action set, we can see in more details that it's a Kubernetes custom resource. It shows that it's using the same Postgres BP blueprint we defined earlier. It's backing up the specified stateful set just as we configured. And it confirms what we said earlier. It used the S3 profile we passed in, connected to the object store with the credentials, and backed up the vector data that we wanted. Now that the backup is complete, let's simulate quickly a disaster scenario. So I'll first connect to the Postgres pod running the PG vector namespace using kubectl exec. And inside that container, I'll launch the psql shell and log in as the Postgres user. Then I'll run the command drop database app. Don't do that if you're, this is just for this demo. But this will permanently delete the application database, the one that stored everything that we had. And if we try to run the prompt that worked before, now it's not working anymore because the data is gone. Luckily, we had made a backup of that. So now we're going to use Canister again to restore the data and bring the application back to its previous state within seconds, you'll see. So the first step is to pick up the name of the backup action set that we created earlier, because everything we passed while creating the backup is stored there, and we won't have to provide those details again and again. So let's get that. And then using canctl, we create a new action set with the restore action. So we had created for backup, now it's for restore. And we'll just reference the previous backup name. And as we can see, the restore action set is created successfully. And when we check the status, we see that it was completed. And the controller ran the task and marked the action set as complete. And then if we take a closer look at the action set, we can see that it's correctly identified and used the blueprint we created before. So let's see that. So it should be Postgres BP. Yeah, let's see the action set describe. We can see the blueprint. It also picked up the target resource stateful set from the backup action set. And in the PG restore phase, we can see the progress hit 100% and it's marked complete. So we can see we didn't need to re-specify anything. Canister did everything automatically for us. And now if we check finally with the data, if the data was restored, we just refresh and everything is working again. Let's check. And great, we can see it's exactly the same as before. So we restored our data and the vector data is available again. The app is responding as expected. So you have hiccups, but you can get back up and running quickly in seconds. So this is, what Canister do for you, and it's very easy. Once you start using it, you learn in, a few minutes. But again, if you have questions, I'll be here throughout the day and available to help show other demos as well. And if you want to connect on LinkedIn for other questions, etc., I'm available. So it was really nice presenting. Thank you so much.
Thank you very much. There is time for one additional question, if there are.
So thank you very much for the presentation, Julia. I have a question. I love this one, Canister. I never heard about that one before. I wonder if we can automate all this one process to make this one available as soon as possible. No?
Yeah, the answer is yes. And even in our blog, we have a lot of people from the community that have done that. So depending on your use case, what you want to do to automate it and, put it in your CI/CD pipeline, you can do that. So the answer is yes. Mm-hmm.
And then there is a lot of what I saw there in the manifest, some of the instruction are kind of more like manual, so that is driven by the technology behind. So this is what is generic for all the other databases, I guess, no?
Yes. Mm-hmm. Yeah. So depending on the flavor of your database, you can manually make different, or you can, automate that as well.
Okay. Thank you very much.
You're welcome.
Thank you very much. Another round of applause. Thank you, Julia.